Okay, good afternoon. Today we are going to start the another chapter of coordination chemistry or inorganic chemistry is Sidwick theory or sometimes called as Sidwick model. In last lecture we saw the optical isomerism of octahedral complexes, tetrahedral complexes and square planar complexes. So Sidwick proposed the coordination chemistry, Werner's proposed the coordination theory, and according to Werner's assumption, the coordination complexes may have the two types of geometry, primary geometry and primary valency and secondary valency. Okay. So, according to Werner's theory, the coordination complexes has two types of valencies, primary valency and secondary valency. Primary valency is ionizable, secondary valency is non-ionizable. Primary valency related to the oxidation number, secondary valency related to the coordination number. Primary valency mostly is non-directional, but secondary valency is directional according to Werner's theory, according to their assumptions. In Sidwick theory, in Sidwick model, according to Sidwick is the scientist and he proposed the theory and called as it is a electrovalency theory. The theory called as electrovalency theory, or it is the it proposed or it is the interpretation of electrovalency of atom or ion, metal atom or ion, means electrovalency. Okay, so basically according to Sidwick theory, it is based on two important points. The Werner's primary valency is it is the electrovalency. It is the electrovalency. Means it is depends on how many electrons are lost during the formation of complex is predicted or interpreted by the Sidwick model. Second, the secondary valency of Werner's theory, it is called as coordination valency. Called as coordination valency. So Werner proposed two valencies, primary valency and secondary valency. But Sidwick changed this theory and says the primary valency of Werner's theory, according to Werner, is the electrovalency of the compound, and secondary valency according to Werner's is the coordination valency. Means here what is the coordination valency of given atom or ion in given coordination compound is predicted on the some terms. Means suppose we consider one of the any complexes and there is a coordination number, means one metal atom or ion has particular coordination number. Question is, why 6 ligands are attached? Why not 5 ligands are attached? Why not 7 ligands are attached? म्हणजे एखाद्या कोऑर्डिनेशन स्पेअरमध्ये जर 6 लिगँड असतील तर तिथं 6 का अटॅच झाले, 5 का अटॅच नाही झाले, 7 का अटॅच नाही झाले किंवा 3 का अटॅच नाही झाले. काही कोऑर्डिनेशन कॉम्प्लेक्सेसमध्ये 4 आहेत, काहीमध्ये 6 आहेत. ओके, तर 6 ऐवजी 5 का नाही झाले, 7 का नाही झाले, 6च का? So it is depends on stability. It depends on stability. We already discussed in stability of the formation of coordination complexes. But Sidwick also proposed this thing. Some complexes are stable. How they stable? We were going to discuss it according to Sidwick model. Okay. So there are two Sidwick model or Sidwick theory based on two things. Primary valency of Werner considered as a electrovalency, and secondary valency of Werner's theory considered as a coordination valency. So for that, here we consider simple example is, suppose here CO NH36 or suppose Ni NH36 2 plus if the complex is formed. So what happened here in coordination sphere, there are 6 NH3 molecules are attached to the Ni. Here Ni present in plus 2 oxidation state. That means here Ni2 plus is present. With that 6 NH3 molecules are present. So why only 6 molecules are here? only 6 molecules are attached to the Ni2 plus and form the coordinate bond. Why not 5? Why not 7? Means how many ligands will be attached? It depends on, so according to Sidwick theory, he proposed the central metal atom or ion accept the electrons from the ligand, how much ligand electrons are accepted till the central metal atom or ion achieve the noble gas or inert gas configuration which is belonging from the same period. म्हणजे की एखादा मेटल किंवा मेटल आयन हे तेवढेच इलेक्ट्रॉन ॲक्सेप्ट करतो ज्याचं ॲक्सेप्ट केल्यानंतर स्वतःचे इलेक्ट्रॉन्स आणि लिगॅंडचे इलेक्ट्रॉन्स यांची जी टोटल असेल ही ज्या पिरियडमधला तो मेटल ॲटम असेल किंवा आयन असेल त्याच्यामध्ये जो लास्टला एलिमेंट असेल इनर्ट गॅस असेल त्याचं इलेक्ट्रॉनिक कन्फिग्युरेशन किंवा त्याचा ॲटॉमिक नंबर अचीव करत नाही तोपर्यंत नंबर ऑफ इलेक्ट्रॉन्स हे ॲक्सेप्ट केले जातात लिगॅंड्सकडनं. So some complexes form 6 coordination complexes, some metal ions form 6 coordination complexes, some metal atom or ions form 4 coordination complexes. It depends on how many ligands will accept or attach to the central metal atom or ion and then achieve the nearest inert gas configuration. So here if we draw the structure of NiNH3 6 we can draw here this way. Six coordination bonds are formed by 6 NH3 molecule with the Ni2 plus. Why 6? Why not 5? Why not 7? Why not 4? So these 6 ligand donate the 12 electrons because each ligand has to donate the pair of electron. So एक ligand एक pair electron ची donate करतो. इथं 6 ligand असतील तर किती electrons donate झाले? 12 electrons donated by the ligands and metal itself, metal atom or ion itself has their own electrons. म्हणजे metal कडे स्वतःचे पण electrons असणार आहेत. Okay, so this is the structure. So according to Sidwick theory, there are two important points. According to Sidwick theory, the primary valency of Werner's theory considered as an electrovalency. And electrovalency means how many electrons are lost by the central metal atom or ion during the formation of complex. Secondary valency considered as a coordination valency. Coordination valency means how many number of ligands will directly attach to the central metal atom or ion. Okay, so for that here Sidwick taking this example, so NiNH3 plus, here Ni present in +2 oxidation state means here electrovalency of Ni is +2 and the coordination valency of complex is 6 because 6 ligands are directly attached. So according to Werner, the primary valency, it depends here how many ligands are there. Okay, so primary valency is different, but here Sidwick consider the electrovalency. Electrovalency means number of electrons are lost by the central atom during the formation of complex. So according to Sidwick theory, in that given complexes, electrovalency is 2 because 2 electrons are lost because NH3 is neutral means Ni present in which oxidation state? Plus 2 oxidation state. And what is the coordination valency? Coordination valency is equal to 6 according to Sidwick theory. So to well explain, to understand the stability of complexes and how complexes are formed, Sidwick proposed the very important phenomenon, important model is, or very important rule is used is effective atomic number means it is a EAN rule. It is a EAN rule or inert gas, sometimes called inert gas rule. Okay, so the important phenomenon or important rule is introduced by the Sidwick is effective atomic number called as EAN rule, or sometimes called as inert gas rule. So according to this rule, complexes are stable or not. So Sidwick predict those complexes which obey this rule is more stable, but there are some limitations, but the theory is proposed and it is applicable in some complexes. Some complexes are well explained by the Sidwick theory. Their stability is explained by the Sidwick theory. We are going to discuss here. What is the effective atomic number? So effective atomic number means it is the sum of electrons of metal atom or ion and the number of electrons which are donated by the ligands, or the number of electron which is gained from the ligands, okay, and number of electron gain from ligand is the effective atomic number, okay, is the effective atomic number. So this is the phenomenon, this is the concept. In effective atomic number, we consider the number of electrons of metal, atom or ion, plus number of electrons gained from the ligands. The sum of these two, if it is equal to inert gas configuration of element which is belonging from the same period, त्याच्याच पिरियडमध्ये जो लास्टला नोबेल गॅस आहे त्याच्या इलेक्ट्रॉन्स एवढे जर त्याचं टोटल होत असेल, दॅट मीन्स ENA रूल इज ओबे. If total means if sum is not equal to the inert gas configuration, that means rule is not obeyed. But in that conditions, sometime if metal ion is used, so if metal ion is used, metal present in ion form means having the some oxidation state, that time we subtract the number of electrons lost during the formation of complex. So how we calculate the ENA rule? ENA rule for the any complexes. So ENA is equal to number of electrons of metal, number of electrons of metal minus number of electron lost by metal, number of electron lost by metal when complex is formed, plus number of electron gain from ligand is equal to how much? If this total is equal to 36 for krypton, 54 for xenon and 86 for radon, that means it is the obeying the EAN rule. Okay, I repeat again. How we calculate the ENA or effective atomic number for given complex? So in complex there are two parts, metal is present and ligands are present. If metal having their own electrons means atomic number, minus when complex is formed, metal having some oxidation state, the oxidation state means that number of electrons are lost by the metal during the formation of complex. So we subtract this number, how many electrons lost during the formation of complex, plus we add the how many electrons gained from the ligand. So it is the twice the number of coordination number. If there are 4 ligands are attached, that means 8 electrons are gained, because each ligand donates the 2 electrons to the central metal atom or ion. Using this formula, we can calculate the EAN number or effective atomic number for different kind of complexes. We are going to discuss it. Okay. Okay, we are going to calculate ENA for given complexes. Here 4 complexes given to you on blackboard. So here, first of all, predict the oxidation state of metal in given complex. So here, in first complex, CO NH3 3 plus. So complex having plus 3 charge, but here neutral ligand is present, means here CO present in CO present in which oxidation state? +3 oxidation state. Predict the first oxidation state of central metal ion. Okay, if there is possible. If not, then oxidation state is 0. Okay, so in given first complex, the oxidation state is +3. That means how many electrons are lost? 3 electrons lost during formation of this complex. Okay, first, number of electrons from CO. So number of electrons of CO, फक्त CO ची लिहायची. आता CO चा atomic number किती आहे? 27. What is the atomic number of cobalt? Is 27. Okay. Second point. How many electrons are lost during this formation of complex? What is oxidation state? 3 is the oxidation state. Means 3 electrons are lost. So here write number of electron are lost by CO atom. किती इलेक्ट्रॉन्स लॉस झाले? 3 इलेक्ट्रॉन्स लॉस केले. ओके. थर्ड पॉइंट असतो हाऊ मेनी इलेक्ट्रॉन्स आर गेन फ्रॉम लिगँड्स. सो हिअर हाऊ मेनी लिगँड? 6 लिगँड. सो राईट हिअर नंबर ऑफ इलेक्ट्रॉन गेन फ्रॉम ligand. Which ligand? You can write here 6 NH3 molecule or 6 NH3 ligand is equal to 6 into 2 is equal to 12. So we have the already numbers. We have the number of electrons of metal 27. We have the number how many electrons are lost? 3 electrons are lost. How many electrons are gained from ligands? Here 12 electrons are gained from ligand. So how to calculate EAN? So here we are going to calculate EAN is equal to number of electrons of metal 27 minus number of electrons lost by the metal. How many electrons lost? 3 electrons are lost plus number of electrons gained from the ligands. So 12 electrons are gained from ligand. So is equal to 27 minus 3, 24 plus 12 is equal to 36, and 36 is the atomic number of krypton. So here the total is equal to 36. That means it is the krypton. That means here obey EAN. So question asked to you whether the complex is obey or not the ENA rule. Justify your answer. So answer is the given complex obeying the EAN rule because the total is 36, which is equal to the krypton. Okay, and how we calculate? The number of electrons of metal minus number of electrons lost by the metal plus number of electrons gained by the metal from the ligands. The total is equal to inert gas configuration. Here is the 36 is the inert gas configuration of krypton. Same way here. Okay, what is the oxidation state? So first of all calculate oxidation state. Here -4 charge. Here cyanide is there. Cyanide is -1. That means here is -6. So how to calculate? We consider X for Fe. Here is the 6 into -1 is equal to -4 because -4 charge on the complex. So X plus